All right, let's look at the Maclaurin series for exponential function, e to the x. All right, so the good thing about e to the x is that it's extremely easy to find their derivatives. All right, so for example, if you have, let's see, e to the x is the original function. And if you take the derivative, it's still e to the x. So no matter how many times you take derivative, you keep on getting e to the x, right? So of course, including nth derivative of f of x, right? So if you're looking for Maclaurin series, if you plug in x equals 0, you get e to the 0, which is 1. So all these derivatives evaluated at 0 are all 1s, all right? So I'm going to just do that. So f nth derivative of evaluated at x equals 0. All right, so following the Maclaurin series formula, we have a summation. N goes from 0 to infinity, all right? Then this nth derivative of 0 is always 1, so you have n to x to the n over n factorial. So you have x to the n over n factorial, right? So that's the Maclaurin series for e to the x. And a simple variation of that, for example, you can find, say, e to the negative x cubed. All you have to do is replace x by negative x cubed. So you will get the summation, n goes from 0 to infinity. Then instead of x, I'm going to put negative x cubed and raise it to the n divided by n factorial. All right, so we can probably write it as a summation. N goes from 0 to infinity. All right, I'm going to separate the negative 1 to the n. And then you have x cubed to the n, so it's x to the 3n power. Then you would have to divide the whole thing by n factorial. All right, so that's the Maclaurin series for e to the negative x cubed. All right, that's it. I hope that this was clear.